minutes, maybe two. Thanks, John. So only maybe 2 or 3 minutes before the seminar. So we have 3 events which are of importance for ARMA. So next week we're gonna have Unconventional Resources Technology Conferences in Houston, and we're gonna have special ARMA session there. And then week after that, we're gonna have the Geomechanics Symposium, or we just call it ARMA, right, in Golden, Colorado. And in February, we're gonna have special ARMA session at HFTC, which is a Hydraulic Fracturing Technology Conference that will be in Woodlands. So a few words about each of those. So the Best of ARMA panel session is gonna be next week in Houston, Texas. And as you can see, our speakers and panelists here, so have some familiar faces here. So if you're going to be in Houston, if you're planning to attend UTEX, so you're encouraged to attend Best of ARMA session as well. Of course, our primary event is US Rock Mechanics Geomechanics Symposium, which this year is going to be in Golden, Colorado. It's a week after UTEX, so it's June 23rd to 26th. So we strongly encourage you to attend this symposium. You're going to meet a lot of familiar faces there. And finally, last but not least, SPE Hydraulic Fracturing Technology Conference. Again, we are a hydraulic fracturing community, so naturally we interact with hydraulic fracturing counterparts of SPE, part of SPE Society. And so they have a call for papers open. So the due date is July 2nd. So if you're planning to submit an abstract, so you have a few days left. And again, we're going to have a special ARMA session there as well. So you're welcome to visit us there. Okay, so thank you so much. That's all I have to share. And so now the floor is yours, Aleksei.
Yes, so thank you, Igor. It's a real pleasure today to introduce Dr. Aleksei Titov. And Aleksei is a senior geophysicist at Fervo Energy, where he's responsible for optimizing enhanced geothermal reservoir performance using distributed fiber optic sensing data. And he's involved in shaping Fervo's research and development strategy. And so Dr. Titov received a PhD in geophysics from the Colorado School of Mines, where he worked on laboratory testing, numerical modeling, and analysis of distributed acoustic sensing, that's DAS data, for reservoir monitoring applications. And during his PhD studies, Aleksei had internships at Lawrence Berkeley National Laboratory, Pioneer Natural Resources, and Aramco Research Center in Houston. And he also holds BS and MS degrees in physics from St. Petersburg University. So it's a real pleasure today to introduce Dr. Titov.
Thank you very much, John. Thank you very much for inviting me for this session. And it would be my pleasure to share some of our work we've done over the last couple of years. Some of this might be familiar to some folks who attend some URTEC, HFTC, but also I will have some new materials to show here. So my talk today is entitled Distributed Fiber Optic Sensing Monitoring of Horizontal Enhanced Geothermal Systems Stimulation, Well Testing, and Production using Offset Vertical and Horizontal Wells. So I will be mostly focusing on low frequency DAS and distributed strain sensing in this talk. I'd like to thank my co-authors for this work, Sirish Dadi, Binakano, and Jack Norbeck. The agenda of my talk today is as follows. I will start with introduction, introduce what are enhanced geothermal systems, distributed fiber optic sensing. Next, I will move to our first commercial project called Project Red, located in Nevada, and I will spend some time there on different data sets we acquired to understand the stimulation and show you how some of this data basically directly affected the well placement. Next, I move to our large commercial project, which we are currently developing just close to Utah Forge. It's called Project Cape, and I will share some results from our recent well stimulations there. and on the right it's just some steam. So yeah, we're producing some energy right now in our commercial project. So what are enhanced geothermal systems? So they're not new, and as you may know, geothermal is not new. It's more than 100 years old. Enhanced geothermal, several decades old. But usually what it was meant under enhanced geothermal systems, it's usually vertical wells with some long-term water injection, cold water injection to stimulate the rocks, and basically we create engineering the permeability in the unpermeable rocks. Because conventional geothermal systems, they are quite limited in the geographical areas, and the resource is basically limited. So the enhanced geothermal system is the way to go to make the geothermal scalable. So what is the Fervo concept? It's basically applying all we learned over the last couple of decades from unconventional oil and gas, meaning horizontal drilling and propped multi-stage stimulation. Here on the right, I have an example of modeled fracture system from our commercial project. And there is a injector and producer wells, as you see. So what is happening, how we harvesting the heat, we inject cold water into injector. It goes through this created network of hydraulic fractures, and we produced hot water from the producer. So what are the main driving factors here? It's basically our resource here is the heat, and our output is proportional to the fracture surface area because it helps with the heat exchange and the flow rate. So that's the two parameters we need to optimize for, is the flow rate through the network and the temperature difference between injector and producer. So what we currently found that the resource temperature we are targeting is about 200 Celsius. Could be a bit more than that, could be a bit less, and that's just basically to run in optimal way organic Rankine cycle power plants. Also, for all our new projects, we are starting with the observation wells, and there are multiple benefits for that, to understand the stress orientation in the field from drilling-induced fractures, to calibrate temperature model, and of course, instrument it with some nice instrumentation such as distributed fiber optic sensing cables. I should say that this approach is very similar to what Utah Forge is doing, and basically we are working very closely together, even in the same location, to optimize this type of enhanced geothermal systems. As I mentioned, our resource is the heat. So what our motivation behind all this data acquisition? So our motivation is to make the resource commercially viable. And for that, we need to achieve high production rates of about 50,000 barrels per day. So frankly, we are talking here not about unconventional oil and gas rates, it's more like offshore oil and gas rates. Large fracture surface area, again, to accelerate and help the heat exchange process. A uniform flow distribution along the lateral. We don't want to connect, some high pathways, some highways with, several hydraulic fractures, which will cool down the particular space pretty fast and will decline, will reduce our life of the resource. That's why we're targeting also relatively small thermal decline over a long period of time. So just to for the context, the thermal decline will be driven by how far away we put injector and producer. The further apart we put in them, we will have the less thermal decline. But the further apart we will put injector and producer, we have a chance not connecting them, so it will affect the flow rate. So that's a balance between flow rate and thermal decline when we're thinking about optimization of well spacing. So following this motivation, we want to optimize, monitor, and characterize the resource. And here I'm talking about well spacing optimization, where we can use, for example, cross-well strain monitoring or microseismic monitoring, completion design optimization, what the optimal way to pump our treatment. And here we're talking about well temperature strain monitoring, slurry prop and distribution, cluster efficiency, stage isolation, and also production optimization, how in long term the resource behaves, microseismic monitoring, flow profiling. And with everything I mentioned here, distributed fiber optic sensing can be very helpful. And I guess the main value of distributed fiber optic sensing is coming not from the single application, but from multiple application over the well life cycle, very similar to oil and gas. And moving to fiber optics, it's still with fiber optics already more than 7 years, but it still amazed me how we can capture all these significant volumes of data and all these beautiful insights from something very tiny. So the fiber optic cable itself consists of multiple fibers, and the fibers are just 2 types of silica glass. And here, for example, I have an example of single mode fiber, and you see that we are talking about micrometers here. So the fiber itself and the data we acquired, and I will present just in a few minutes, it's coming from this tiny piece of glass. And of course, there are significant benefits of using fibers and fiber optic based sensing in geothermal applications, because as you may know, we're struggling a lot with any electronic tools downhole due to high temperatures, but fiber, it's really, if protected properly when we put it to the cable, it can withstand very high temperatures. And for geothermal applications, we use so-called polyimide coated fiber. It's just this coating which protects the fragile glass, and we can easily use it for multiple years, up to 300 Celsius, and there's different types of coating which allow us to push it even further. But all our resources, as I mentioned, targets in range of 200 Celsius, so that's why we're using this polyimide coated fiber. And also, when you see in this construction of the design, for our goals, when we're talking about strain measurements, we need to understand that we're measuring strain along the fiber, and this fiber, it's actually usually inside the gel filled tube. So we're not measuring per se the rock strain, but and I will show the types of installation we're using, but we're measuring what is captured by the fiber itself. So there could be some transfer function, and it's still pretty hot topic in oil and gas community as well, how to understand what are the frequency ranges and what's the transfer function, what's the effect on amplitude of the measurements due to the cable installation. There are a couple of different types of fiber optics, single mode, multi-mode, but basically for broad audience, single mode we're using for distributed acoustic or strain sensing, and multi-mode for temperature sensing. And how it works, it's basically very cool. It's very nice physics there. It's basically a scattering of tiny portion of the lights. There is an interrogator unit on the surface which connected to the fiber. There could be some surface portions and downhole portions of the cable. And when the light is propagating through the fiber, it scatters at every point of the cable. And there are different types of scattering, and ultimately using inversion from this scattered light, we can measure very sensitive with very high sensitivity acoustic, dynamic strain, temperature, and I'm talking about here low frequency DAS. It's nanostrains per second, so it's very sensitive. It's almost atomic level sensitivity there. Crosswell low frequency DAS or strain sensing is not new. The initial research started in 2015-16. There is a great paper by Jin and Roy, which introduced this concept and method to the broader community. Basically, if you have the fiber optic cable cemented behind the casing, and if there are any strain changes along the fiber axis, we can capture them. Again, as I mentioned, it's very sensitive to any strain changes, either mechanical or thermal, and we can invert fracture properties from that. And this is from horizontal well, so it's when we have horizontal stimulation well and horizontal observation well, and it's commonly used nowadays in oil and gas in production, especially with some single-use fiber technology, which is cheaper than installing permanent fiber cable. You can easily understand the frag heat, volume to first response, azimuth propagation, and anything, even like if you have any plug leakage in the previous stage. So it's I would say it's already very well established method on resource characterization. And here's some examples from HFTS2 dataset where the vertical measurements were introduced. And it's basically the same principle. If in horizontal configuration, we measure epsilon XX component along the fiber. In, for example, horizontal to vertical configuration, we measure epsilon ZZ component of the strain tensor. So again, we are measuring strain change along the fiber axis. That's what we are capturing here with this data. And there was really nice results from HFTS project. Moving back to the Fervo assets and our way to acquire this data, we have, I would say, very significant compared to probably HFTS program on the data acquisition, because of course that's quite new to stimulate the rocks we are stimulating in the environment we are located. So for our first commercial project, we actually installed permanent fibers in all our wells, and I will with some success, variable success on the surveyability of the cables. So when we install in fiber optic cable, you see here, that's our production casing. So fiber is clamped lower down and cemented in place. And I would say that cement portion of all the installation is one of the most important, because the better cement quality, the higher the chance that the fiber cable will survive during the operation. Other types of installation, which we trialed in our second project, again with a very success rate, is a wireline fiber deployment. So in this case, if we have a well which has top port opened but not completed yet, we can pump on the tool. And here we have a fiber cable going to the wellhead for a lubricator, and we can deploy it almost to the TD of the well. And another technology, which is again very popular now in unconventional, is so-called single-use fiber. In this case, as I mentioned, the fiber itself is very tiny, and 18,000 feet of fiber is basically spooled in this small shuttle. And after that, the well is opened, and again we can drop it initially, and after that we can start pumping on it and deploy again to the TD. However, I need to mention that our resource temperature here is up to 10 to 20 degrees Celsius. So this was the trial of underrated fiber, more than 70 degrees Celsius underrated fiber. But yeah, that's different types of deployment. In this case, the strain transfer would be the best. Despite that we have some gel inside the cable is cemented in place, so whatever strain change the rock experienced, almost the same strain change will be experienced by the fiber. When we have a wireline installation, it becomes a bit trickier because now the fiber is coupled by gravity, and it depends on the weight, condition of the wells, if there is any doglegs severity. So it's not ideal for strain, especially low frequency strain measurement. But still, there are some multiple successful examples from unconventionals. And when we're talking about single-use fiber, we have some grease inside this tool. So the fiber itself, it's very light. It's basically like a hair, or some people say it's more like a dog whisker. So you can imagine now this fiber is laying in the well, and the hope is that by gravity it will be going to the bottom of the casing and stick with the adhesive to the casing, and that's what providing the strain coupling there. And again, there are multiple successful examples of this technology for cross-well strain measurements. On the equipment needed in addition to the fiber itself, it's the interrogators. Here I have set up from one of our vendors. That's a lot of computational equipment, and the interrogator itself, it's a laser plus photo detector system and computer. So it's pretty cool tool, and also we need powerful processing to do some edge processing, and some, I would say, novelty to acquisition of the fiber optic data. We have a lot of fiber optic equipment in-house, and that's basically driven to a bit different approach from unconventional oil and gas. Unconventional oil and gas usually measure acquiring data only during stimulation, but we are very interested in data also during cross-flow test, injection test, production. So that's a system we currently have in our commercial pilot project in Nevada. So it's running 24/7, already more than a year and a half, constantly acquiring data for us to understand the resource better. Now moving to the project Red. That's what I mentioned, first commercial project, which is currently powering some Google data centers in Nevada. Here on the left, I have a summary from Jack Norberg's presentation during our technical day, and you can find this presentation on our website, as basically share a lot of details on our well design as well as stimulation design, which remains quite similar for the following projects we have. So what are the main highlights here? This is the geological model, and you can read more about the geology from Steve and Fervo papers, both on Red and Cape project I will talking about later, from Stanford Geothermal Workshop, really nice papers, a lot of details there. But the main things here is the lithology. So we have phyllite, quartzite, diorite, granite. That's our basement, and that's our reservoir. So that's pretty hard rocks there. And here you see our project Red setup. So first we drill this observation well called 7322, about 8,000 feet deep. This well will equipped with fiber optic cable and also pressure temperature gauge behind the casing. And it was really useful well to understand the temperature distribution, to calibrate this 3D temperature model, and you see the contours of the temperature in the background. So the hottest portion of our well is reaching about 370 Fahrenheit. and there is some distribution of the temperature along the lateral. After that, based on some data we acquired from our observation well, we drilled our injector well, which is 34A22. I will call it ING injector, and it's targeting lower depth of about 700 feet. We stimulate this well, recorded the stimulation in the observation well, and the low frequency DAS was a huge portion of the decision how we want to place the producer well after the injector well was stimulated. And the production well, which for 22, is a bit shallower, and I will show you some details on the spacing on the next slide. Other things to note, it's a 978 production hole with 7-inch casing. Again, we are more talking about offshore type of wells here, very large bores. Permanent fiber optic cables were installed in all 3 wells. As you see, it's quite complex build to these wells. I think it's one of the first horizontal wells drilled in these conditions, fully horizontal wells. On the stimulation treatment, we have 16 stages in the injector, 20 stages in producer, 30 feet cluster spacing with 6 clusters per stage, 180 feet stage length. And I would say on the higher side of the conventional and unconventional stimulation treatment with 500,000 pounds of propellant per stage, 4070 and 100 mesh propellant, and 100 barrels per minute target rate. So pretty large stages here. Everything went. We were able basically to achieve these conditions during our treatment. A bit on the distributed fiber optic sensing data acquisition and the spacing of the wells. Here's a map view and section view of the wells. Also, you can see in the background the lithology. And as the producer well was drilled after the injector well being stimulated, you see also some propellant detection from mud logs, which was really nice to see and confirms the decision on the well spacing. On the data side, again, a lot of data was acquired. I will be mostly focusing on the crosswell data here and mostly strain data because that's portion within the team I'm mostly working on, and I will touch a bit on microseismic data as well. So what I will show you next, some examples from our data acquisition, and namely the injector stimulation recorded in observation well, some interesting results during injector injection test. So in this case, we were injecting to the portion of the injector without flowing producer and measuring the strain in the producer during this injector injection test. Producer stimulation again recorded in observation well, and some results from crossflow test again recorded in observation well. Unfortunately, there were some setbacks. Again, it's a first of a kind project, so we lose some fiber during treatment of the injector well. Actually, it was the erosion of the fiber cable, and I guess the reason was due to cement drop and some channeling. We were not perforating through cable over about 1 hour into one of the stages. We noticed a lot of vibrations above the cluster, and that damaged the cable, and after that the damage propagates further because again it's a thin fiber and metal tube. As soon as we have some pressure communication to this metal tube, fiber can be pushed further closer to the surface. And with producer well, we have some casing damage during one of the first stages being stimulated, and that's basically also damaged the full extent of the fiber in the producer. So we were not able to get low frequency DAS or distributed strain sensing data during offset well stimulation, let's say producer recorded into injector well this time. That's a typical response we have from the stimulation recorded in vertical observation well. Again, here is a measure depth, that's the time of our treatment, and we see all this nice response here, which, as I will show you in a bit, related to the fracture height. Also, there are some interesting, stripes here, and as we found, that was from some geophone array which was installed, and there was some active heating occurring, active cooling, which basically creates heat on the fiber. And yeah, these stripes are thermally related, which was pretty interesting to see. But let's focus on the main response here, how we can use this data to gather some interesting, useful properties. Again, that's not really new to the industry. Great work by ECFRAC consortium done on the estimate of the structure properties from vertical well observation using HFC data. Basically, as you see here, we can use a polarity flip between extension and compression to at the end of the treatment to estimate the fracture height. I would say it's the measuring fracture shadow height, but after that we can invert for fracture height. And I want to show you some modeling we've done using ResFrac software. Basically, what is going on here, we are viewing from the side, the section view. You see some fractures appearing here, and that's basically a history matched model from our treatment. And what I'm plotting here is the strain change vertical component of the strain tensor. So that's basically what we're measuring with the observation well. Here we were modeling the middle stage and the observation well located here. But what I want to mention that basically using just one model like that, we can explain to some degree the response for most of our stages, because the sizes here is about 3,000 feet, the lateral extent. The fracture height here is about 700 feet. And if you're doing just slices of this plane, it's basically what we get in the response in the fiber. So, for example, for the TOS stages, we will be slicing this plane here. And basically, as we move in from TOS to heel, performing our hydraulic fracturing stimulation, we basically just slicing across this strain change distribution. And I think that's pretty important to understand, because that's basically what we're measuring here and what we're trying to analyze. So as we come in closer to the stage being treated with our observation well, or in the real case, when our stage is coming closer to the observation well, we get in the estimate of fracture height, which we derive in using this polarity flip between extension compression phases of this stress shadow response. We basically get a very good fracture height estimate. When we are further away, we are more measuring the fracture shadow height, which need to be calibrated, for example, using this type of modeling to invert for fracture height. And that's what I will show you in the next couple slides. Here it's a bit more on this modeling, just again the same distribution of the change of vertical strain. And we also use the estimated from drilling-induced fractures azimuth here. And that's also pretty interesting, because now when we see how the response looks, for example, in this horizontal plane, again, we are slicing through this component of the strain tensor, we see that the azimuth will lead to some asymmetry in the response if we basically moving from toe stages to the heel stages. So there is not only the change in the height of the shadow, there is also a change in amplitude or magnitude of the response of the strain or strain rate, which we measure with the fiber. And actually, that's what we've seen in the real data. So again, over here is the field data. This is some model data. What we measure here is pretty straightforward, is the polarity flip at the end of the stage. We have recorded shadow height, we have model shadow height, and now we can use the model shadow height and the actual height we put into the model to do calibration and extract the height of the fracture. So that's what was done here. On the top, you see the recorded response. On the bottom is the model. And I would say it's a very good match. Again, we use ResFrac software here. So we see the main trends, like the reduction in the shadow fracture height, which actually it's only due to geometry. The actual height we put into the model, they were quite similar. And after that, we have the vanishing response for the stages, for the hillmost stages, and it's because the azimuth. So what we can derive from that is not only the height properties. So here we estimate about 400 feet half height. And unfortunately, we were not able to capture bottom half height because the well was not deep enough. But also the nature of response suggesting that the fracture growing to the observation well, which is about 800 feet. So we can have some estimate on the fracture length. And also the nature of the response, the amplitude of the response, suggesting the planar fracture propagation. So the response becomes higher and higher for the when we come in closer to the middle of the treatment, and it's also suggesting the azimuth. So I would say the match between model and the recorded data is pretty significant here, and I was really glad to see that. Based on this data, the estimate of fracture height, fracture length, and of course we use other data set, microseismic pressure data, history matching of the models with the pumping curves. We decided to place our producer 200 feet vertical, shallower, and 400 feet lateral spacing. So that's a direct impact of this data to our project development. Next, let's move to our injector injection test. So a bit of background here. The all wells drilled. Injector well is stimulated, but only 7 plugs were drilled out. So we injecting into portion, the hillmost portion of the injector well. The producer has fully coverage of the fiber optic to TD because we haven't stimulated. There is no damage to the fiber yet. And here are some rate and pressure curves for the injection test. And this is the measured depth and time, at the same time as for these curves, and the strain change measured using high resolution Rayleigh frequency shift distributed strain sensing. And what we find out that there were some nice response even before we stimulated producer. There are definitely a hydraulic response from the induced fractures, which were being induced during stimulation of the injector. And also the timing of the response aligns very nicely with the pressure at the wellhead of the injector, which suggested very good connectivity. So even before the producer was stimulated, we demonstrated that we are connected. And of course, I need to mention that we also saw propant during drilling. That's of course much more direct suggestion that we are drilling truly through simulated reservoir volume. So there's a zoomed in version and some interpretation. So there was some processing. We stack the strain change, gaining just cumulative strain after the shut-in, and there are multiple zones identified in the producer, which can be associated with the fractures being opened and aperture being changed as a result of the injection test in the injector. When we wrapping up the rates, the aperture increases. As soon as we shut down, the aperture decreases. There's some stress shadowing going on the sides of the fracture, but this data set, we are still working with our academic collaborators to gain even more insights from this. And also I need to mention that we haven't seen any response below the undrilled plug, which might suggest that the plugs were still holding. And next, let's move to the producer stimulation. Very similar data set here. I'm showing you full 8,000 feet recording. And initially, yeah, it was very similar, but after that we have this response. And initially we were a bit struggling understanding what is going on there. We're not suggesting that we have 8,000 feet, fracture mechanically interaction, and the DTS data was really useful here. So I already mentioned here fluid column movement, and that's actually what happened and confirmed with the DTS data. So what happened here when we were pumping stage 10, it occurred that our plug in the vertical well failed, and we start pushing fluid into our observation well. Initially, the water column was lowered down to 1,500 feet from previous acquisition when we were running geophone stream. They usually do it to remove some surface noises, and strain data and also temperature data suggesting that this fluid column was moving. And when the fluid column moving, there is some temperature change because, of course, we have a thermal gradient, and for example, this portion becomes hotter, this portion becomes cooler, and that's what the strain, again, we are very sensitive to any strain change here. So that's basically all the signal was temperature related, as was confirmed by DTS data. So some lessons from there, we need to have a very good insulation of our observation wells. And comparison side by side for the similar middle stages. What we observe for injector and producer stimulation, it's very interesting. So we have very similar responses. The upper boundary you see in the measured depth is about 7,200 feet, and it seems when we were stimulating producer and injector, we basically there could be some stress barrier which prevents further growth of the fracture. And also for the reference, I have a relative location of the relative depth of the injector and producer wells here. But again, very similar response. Very nice. We can pick the fracture height and estimate from there. So the estimates for the producer stimulation was very similar to what we estimate for injector. And just a side note here that the data might be used not only for height estimation, there are much more in the data. For example, here we see as we start pumping in our type of propant, it seems we're not changing the aperture much, and actually the fracture might be even start closing here. So again, there is much more details in quantitative analysis, how this vertical observation well data can be used not only for height estimation, which we currently, I would say, routinely doing with such data, but there are much more detail in that. For example, the distribution of the amplitude along the vertical axis might be of interest as well. And now let's move to our crossflow test or production test. It was a 30-day crossflow test at Project Red. And there was some interesting, what we call Fervo flag cycles, when we keep injection rate stable, but we actuate in the producer and almost until the full shut-in of the well. And it's occurred that this shut-in of the well has very similar response in the low frequency DAS, similar to what we observed during stimulation. And that's basically suggesting that the fractures which are close to observation well, they remain active, and the height again can be estimated for this active reservoir volume, what we can call it. On microseismic side, pretty nice data. And here are some distributions on the microseismic. They're a bit telling different story from the low frequency DAS, and I think it's just due to nature of what we're measuring with microseismic. It might not be the fluid path or propped lens, but some stress, local stress changes which lead to the triggering of the events. And to learn more about microseismic, I would refer to our paper by Sirish Dadi at Stanford Geothermal Workshop this year. And now let's move for next 5-7 minutes to the project Cape. That's our main project. It's set to deliver 400 megawatts. A lot well already has been drilled and much more to be drilled. We are located very close to Forge and really appreciate all our collaboration going on data acquisition and all other aspects. The stress orientation you can see from here. It's a very nice paper by Steven Ferho at this year's Stanford Geothermal Workshop. Very similar in general to Project Red, higher length of the laterals. Here we have only fiber optic installed for now permanently in this Delano observation well. The temperatures are a bit higher, going up to probably to 10 to 20 Celsius, 420 Fahrenheit to some portions of the well. And also we learned some lessons. Our observation well is now deeper, so we can measure bottom half height of the fractures, and also we didn't do any defeats on the well, so it's fully insulated. We do not expect any thermal or flow breakthrough to the observation well. And here I just want to quickly share some of our recent data from our single-use and wireline fiber trials. On the left, you see microseismic data quality. I was really amazed by wireline data quality which we installed in Frisco 2P. This is high-temperature wireline, and as you see, microseismic quality is very similar to permanent fiber we have in Delano. So it was really great to see and real success on the microseismic side. Single-use fiber, even in vertical section, was providing some data, and of course not so clear as wireline or permanent, but it was also pretty nice to see. On the low frequency DAS, it was really challenging. There are a lot of stress relaxation in wireline, probably due to temperature difference when we pumping on the fiber, and it's still there. We are trying to analyze this data. There are some reactivation and probable reopening or passing of the fractures from the low frequency DAS can be seen, but the data is very noisy, probably due to this relaxation of the fiber and the coupling. The single-use fiber did not last too long. I think we installed it, and after about 20 hours, they installed before stimulation. After 20 hours, it being installed, it detached from this shuttle and start degrading in the horizontal portion of the well. So we were not able to capture any low frequency DAS with the single-use fiber. But again, it was trial, it was underrated, and we're working with the vendor to understand how we can modify it. I think the main issue here is the temperature differential. We need to pump on the tool, we're cooling down the well, and after that it starts rapidly warming back, and that might lead to the damage of the fiber, even if it would be higher rated fiber. But some work needs to be done here. Here is the zoom-in version of our wireline deployed fiber. Again, it's horizontal measurements and green boxes. It's expected fracture arrivals for different stages. And yeah, the data is noisy. There are some interesting features which we are still trying to understand. It might be reactivation of some natural fractures or faults. But generally, yeah, there is some propagation of the signal as we propagating from heel to toe. So for the reference, we were stimulating this blue well, 1i, and the wireline was deployed in this orange well. On the observation well, vertical observation well, the line is much more cleaner, really nice data set. And basically the same analysis can be done as for previous Project Red. We see how we pump in different stages at the fracture heat into the Delano well from 1i. So it's suggesting that the fracture length is more than the distance between 1i and Delano, which is 800 feet. We can pick again for some stages the height, and we estimated that it's about 700 feet total height. Very nicely can be picked, for example, for 3i when we're closer to the observation well. Amazing data set, still to some work to be done, especially on the middle stages where we have an interesting interaction of the different fracture openings. Probably there are some features intersecting well, but yeah, we were able to determine our fracture height. That was the main goal of this data set, and it's aligned with our models, so we are pretty happy with this data. So some takeaway messages. Crosswell distributed fiber optic sensor is a really valuable tool for geothermal wellfield optimization. You see, we are almost routinely using the fracture height estimate to calibrate our reservoir engineering models and guide our decision on well spacing. Data we used also to understand the fracture behavior, and it's suggesting mostly planar fracture propagation. And due to elastic properties of the rock, we have seen the very clean data from stress shadowing even 2,000 or more feet away. Some way forward, more data to acquire, especially in horizontal wells with permanent fibers, or mitigate some issues with the temporary deployment on the low frequency DAS, RFS, DSS. We are looking forward to the Forge data, which was acquired recently, to see how it looks like. I think it should be very nice data there. And also working with our collaborators, ECFRAC, Texas A&M, RCP, Colorado School of Mines, top-notch groups on this type of data to learn more. And with that, I would like to acknowledge everyone at Fervo Energy, really great team here. All our contractors and service providers, without them, it would not be possible to drill, stimulate, record data. Our academic collaborators, Colorado School of Mines, Lawrence Berkeley National Lab, Rice University, Texas A&M. Really enjoyed working with these groups on this data. Our industrial collaboration, Devon, ResFrac, of course, Utah Forge, and government funding from DOE, ARPA-E, and Utah Forge. With that, I would like to thank you all for joining this morning, spending some time learning more about fiber in geothermal. And I'm open here to questions.
Thank you, Aleksei. What a great success story, or stories. We do have a few questions. The first one is pretty straightforward. It's a clarification question. What does the abbreviation ARV stand for?
Yeah, that's something new abbreviations we are coming with. That was suggested, I guess, by Dr. Wu. We called it active. You know, there is a drained reservoir volume in oil and gas. We call it active reservoir volume, and basically it stands for what remains active during production.
Okay.
But I'm open to any other suggestions how we can call it.
No, that sounds reasonable. A question from Mohammed Gabri, and he's wondering about the availability of your data for use by universities and other entities.
Very good question. I mean, we are open to collaborations. We are part of RCP consortium, ACFRAC consortium. All data acquired by Forge is public, so that might be very interesting to look into. Even when we stimulating and Forge acquiring, that should be available for GDR. And if there is any particular project of interest, please feel free to contact us, and we are more than happy to discuss.
The next question is from Eileen Zabrowski, and Eileen would like you to explain why the wells are offset horizontally and vertically.
A very good question. So there was some modeling done, and I think it's some advertisement here. There will be a nice tech course on geothermal reservoir modeling by ResFrac and our reservoir engineer at URTEC coming, so you can learn more there. But the goal here is basically to have additional time for the cool water going with density a bit to deeper portions, and after that return to the producer. So that's a vertical offset explanation, just to give a bit more time for the molecules to perform heat exchange.
Now, Nicholas Urado, Nicholas is interested in what your thoughts are on the permeability or conductivity for these fractures and whether or not it's held up during some of your injection operations.
Yeah, to some values I would refer to Jack Norberg Latimer paper. There's some estimation on conductivity, but as far as I think it holds because that's what we've seen from even this data. Our active reservoir volume ARV remains very similar to SRV. So, and our production, we're producing our commercial pilot project already for more than half a year. I think it's 8 months. There's basically it behaves as was modeled. So it means that the conductivity holds.
Very good. Then Andres Chavarria. Andres would like to know, in regard to your low frequency DAS, you mentioned the model was matching the observations in magnitude, and he's curious if you could quantify that in terms of average microstrains.
Yes, that's a really good question. I think it's about we are modeling strain rate, and for further stages, it's about nanostrains per second. For the close stages where we have frag hits and interaction, it could be up to 30, 40 nanostrains a second. And it's not like perfect match. I was mentioning more how the magnitude changes with when we come in closer to the well. But I think and that's something we're working together with ACFRAG to, do a fully quantitative matching and inversion.
What would like you to speculate whether you can attribute late time strain to viscoelastic behavior in the rock or fluid leak off redistribution? Any thoughts on that?
I fully understand the question. I guess late time behavior if something is propagating after we, for example, stop in fracture, or if I'm not correct, please correct me. But yeah, we see some delayed pressure increases in offset wells after we, for example, stop the treatment. Some of the data from the recent vertical observation well, for example, we stop our stage, but we see some growth. So we've definitely seen some processes like that.
Pradeep, what is the measurement control parameter to determine how many fiber sensors to deploy in real-time conditions?
I mean, that's basically the fiber sensor. It's a distributed fiber optic sensor. If we're talking about the cable itself, we are optimizing for something like gauge length to provide whatever is necessary for the special resolution, and that's what we can call sensors or channels in the fiber. So that's currently we are not targeting very high resolution. We're more interested in something like 50 feet resolution, especially for observation. Vertical well. For horizontal wells, there could be some optimization. It should be less than cluster spacing if you want to see separate clusters. And that's where, for example, radio frequency shift DSS might play a role, which has higher density of these sensors. If we're talking about sensor as a well, that's another thing to optimize where we want to place the observation well, or what the type of observation well we can do. There really great work by industry. I think Exxon, Conoco, other doing on the slant well monitoring, which can sense the structures away from the stimulation well and in different depths. So that's something we're also looking into. That's pretty cool to have such data. So yeah, there are multiple parameters. Hope I answer your question to some degree.
You know, I'm afraid we've got good questions, but what I'm going to do is, if it's okay, I'm going to copy the chat and forward it to you, Aleksei, and maybe you can interact with these individuals individually.
Thank
just
you. And please reach me out also if you have any questions.
Yeah.
Either through email or LinkedIn.
Yeah. I think Yingping Li said it exactly in his comment. Thank you for a very impressive presentation. And thank you, Aleksei. And we look forward to watching for future success at Fervo.
Thank
So
you
thanks,
very much.
everyone.
Thank you.